Hello, this presentation is titled Sparse Matrix Neat Examples in Raku. My name is Anton Antonov. Today is October 27th, 2024. I assume most of the audience of this presentation is familiar with the concept of sparse matrix. So here you see a random sparse matrix. The rectangles, the squares in black represent elements which are zero, and the colored ones which are non-zero. So the data structures used for sparse matrices, they allow efficient representation of matrices that have mostly zeros as their elements. Instead of a zero, we can have any other value, but it is a constant. So basically, majority of the elements are this constant value. All right, so in this presentation, we're going to look into three sets of examples. The first one comes from an adjacency matrix of a random graph that is produced from a model of social interactions. The second set of examples comes from a movie actor graph, so actors starring in certain movies. And the third set of examples is about visualization of random matrices. I would like to point out that for me, and this is a personal opinion, the sparse matrix linear algebra support is a sign of maturity of the corresponding system. And you can see different popular systems for technological computations. They have introduced sparse matrices at different years. All right, so let's look into the first example. This random graph with the Watts-Strogatz model. I especially made it small. If I want to be kind of more interesting graph, I can make it larger. But let's use this small graph. I have also found the shortest path between 0 and 12. This is the subgraph here shown in orange. And here is the corresponding sparse matrix. So this is a visualization of the sparse matrix. So this is adjacency matrix, which shows which edges are connected in the graph. And the non-zero elements in this plot were with this bright yellow color, and the zero ones with this black color. So the way this has been created, it is showing that there is an intimate relationship between graphs and sparse matrices. So we're going to exploit this in this example. So here I'm going to make another sparse matrix based only on the path, right? On the path, shortest path between 0 and 12, which I was mentioning earlier. And I'm going to add these two matrices. This addition is element-wise, so in order to visualize it. So you can see here, this is the original graphs matrix, and this is the one for the shortest path. The matrices are symmetric because the graph is undirected, right? And so one thing I would like to mention is that this matrix here would have been much smaller because the path graph has only 4 vertices and 3 edges, but it is having this form because I imposed these row names which correspond to the original graph matrix. And if I add them together, I can have this representation in which we can see all of the edges. So each entry of this adjacency matrix represents an edge, each non-zero entry. And the ones in yellow here on this plot corresponding to the path, and the ones in, I don't know, purple, they correspond to the rest of the edges. So you can see here I have this piecewise operations, sorry, not piecewise, element-wise operations between the matrices. So I can multiply with a scalar a certain matrix, and I can add that matrix to another matrix. Of course, for this element-wise addition between matrices, the dimensions need to be the same. Hence, why I was showing that the row elements here, row names correspond to the path matrix correspond to the original one. Okay, the way I'm multiplying this is because this gives me a very nice or easy way to manipulate the colors in the visualization. Let's actually look into some more into this. So I can have this pretty printing of the sum matrix here. So you can see it with the latest multiplication and addition, how it looks like. Another thing I can do is that I can compare the graph and the matrix. So I'm going to walk through this here. So the first vertex of the path is 0, so we can see that 0 connects with vertex 6. This is what you see here. Now 6 connects with 10, and this is what we also see here, 10, 10, and 10 connects with 12, no, vertex 12. All right, so this was the first example. Now the second example is using the data of certain popular movies in the past. And these are actually, let me just show the summary here, and I'm going to zoom out. And so we have Lord of the Rings, X-Men, and Pirates of the Caribbean, and the corresponding actors. And so I'm going to create a bipartite graph. And so we can see, let me actually show how the bipartite graph looks like. So the bipartite graph, the name bipartite means that we have two sets of vertices. You can see here in red the movies, in orange or yellow, orange I think, the actors. And the bipartite graph here, after it has been created, this is it's a very simple creation. I took the original data set and I said, well, the movie connects to the actor. The graph is undirected, and I can also verify that this graph is bipartite with some of the functions of the package graph functionalities. I can actually show what are the colors. I can the package itself graph has functionalities for coloring the bipartite to do bipartite coloring for the bipartite graphs. Okay, so. What is this though? So what, right? Okay, let's actually show the sparse matrix here. And I'm going to create the names for this in the following way, the names for this sparse matrix. I'm going to take all of the movies and put them in the front. And then I'm going to list all of the actors. If I just create the matrix from the graph itself, we cannot exactly see that this is bipartite. At least to me, it's not clear, it's not obvious. But if I use this way of reshaping the matrix, so I'm using the names I mentioned earlier to reshape the matrix, and now it's very clearly bipartite. Why? Because these edges, these vertices here, they don't have connecting edges to the second half, to themselves, sorry. They only have connection edges to the second half of the second part. And so similarly here, the vertices which correspond to the actors, they do not connect to the movies. This can be also visualized through an HTML, and here I need to zoom out again. So in this HTML representation, you can see how I have rotated in vertically the column names. And so again, you know, we can see how the movies do not connect to each other. Movies connect to actors, actors connect to movies. So as I said, clearly a bipartite matrix, this is by definition. So if I look here in the graph, say if I show this, the red vertices, they only connect to the orange ones, and the orange ones only connect to the red ones. So by definition, this is what bipartite graph is. Okay, so next actually I'm going to show the fundamental information retrieval operation. This is one of the reasons why sparse matrices are very useful in data science, in machine learning, and information retrieval. So first I'm going to take a vector which corresponds to Orlando Bloom. So let's actually find Orlando Bloom here. So you can see this is the vector here. So this vector is about the movies in which Orlando Bloom participated. Now if I multiply that vector with a matrix, what is going to happen? And with the original matrix for the bipartite graph, this is going to give us the actors with which the non-zero elements of the results are going to give us the actors with which Orlando Bloom participated in movies. And so say you can see here that he was in 5 movies, right? Orlando Bloom and Orlando Bloom. But with the rest, like say Johnny Depp, he was in 3 movies. This is the Pirates of the Caribbean movies, and so forth. Again, this is a very, very useful operation. This is this functionality to have these functionalities, to have a sparse linear algebra with named rows and columns for the sparse matrices, makes it very easy to have different types of information retrieval and data wrangling and data manipulation, you know, in the system you're using. Okay, so the last set of examples is with I said with random matrices, but not only random matrices. I'm going to use the bipartite matrix again. I haven't found yet a nice way to display to automatically display the tooltips, or automatically derive and display the tooltips. So there's a display of the tooltips. You can see them here by default. Let me see, do I have the default here? By default, as a dense matrix, the tooltips are just showing the value of the corresponding entry, but it would be nice, especially with the sparse matrices, it would be nice to kind of show what are the corresponding rows and columns, especially if the rows and columns are some long names like what we see here. Okay, I can use these tuples in order to facilitate the plot with using list plot. This is a very simple plot. It's not as elaborated. These are rectangles, and you can see the rectangles, they also have borders and so forth. So this plot can be, as I said, can be very simple, and it can be very useful for large matrices. And this is, no, I didn't want to show this, but let me actually show the large matrix example since I mentioned. So this is a matrix which is with 200 vertices, and again I'm using the Watts-Strogatz display, and this is how it looks with tuples. If I increase the number of vertices, right, like say 2000, and this is going to be, yeah, a fairly big matrix at this point. You can see we have nearly 9,000 non-zero entries. This JavaScript visualization, it basically has an array of 9,000 dictionaries which specify these points, and it happened relatively quickly. I'm not going to do that with this plot, which actually uses the matrix plot, because it's going to be way too slow. Okay, so my last example is with a random matrix. So you can see here, maybe I should zoom out. Let me see. Yeah, okay. Yeah, I basically generate some random dense matrix, and I randomly select what to order the rows or to order the columns, and then I randomly select the actual color palette which is being used, and then we see this kind of example. Matrix plot comes from JavaScript D3 package. It is somewhat independent from the sparse matrices. So I try to make these packages independent as much as possible. GS D3 matrix plot, yes, it can use specifications of both dense and sparse matrices, and here we're using a dense matrix to do the visualization. I mean, above you can see I have variety of ways of showing sparse matrices. All right, this was it. Thank you.